Hi viewers, in this video we will solve problem 5.4 from the book McConkey and Td Eastop. So the statement of the problem 5.4 is a closed cycle gas turbine unit operating with a maximum and minimum temperatures of 760 and 220 centigrade has a temperature ratio of 7:1. Calculate the ideal cycle efficiency and the work ratio. So you have a closed cycle gas turbine, that is I have drawn its schematic diagram, and I will write stage diagram also to make it more valuable for understanding purposes. So let me draw first the schematic diagram. So that is already drawn. Now to make its stage diagram, let's make it. So for TS diagram, you know that gas turbine work on a constant pressure cycle. Okay, two constant pressure cycle and two isentropic processes. So the process, so it's a TS diagram. So the process that is taken from 1 to 2 is isentropic compression. Okay, and the process that is taken from 2 to 3 is constant pressure heat addition process, that is the constant pressure heat addition process. And then 3 to 4 is isentropic expansions, that is done by this turbine, the help of this turbine, and delivered you the work output. So here you will get the work output, and to run the compressor you need to supply the work in to the compressor to run the compressor in order to compress the working fluid from process 1 to 2. So here you need the work supplied, so you denoted by WC. And the process 2 to 3 is the constant pressure heat addition process, so here you denote by Qin. And this is the heat rejection process, here the heat is rejected by this cooler. So that is heat rejections. You can call it WQR, and it is Qin. Okay. I hope you understand the Brayton cycle, on the basis of which the gas turbine work. So let's come to the statement of the problem. So a closed cycle gas turbine unit operating with a maximum and minimum temperature. So the maximum temperature is here T1, that is the minimum temperature, that is 20 centigrade. If you convert that into Kelvin, just add 273 with it, so it becomes 293 Kelvin. Next is the maximum temperature. You know the maximum temperature will be found at the point T3, because here heat addition is taken place. So when heat is added, the maximum temperature at the cycle you will get, that is at T3. So T3 is 760 centigrade. Just add 273 with it, and you will get 1033 Kelvin. Next thing that has been given in the statement is the pressure ratio. So the pressure ratio that has been given to us is 7:1. So it means that the pressure P2 by P1, P2 by P1, this is a constant pressure line. Remember, this is a constant pressure line, and this is also a constant pressure line. So and the pressure ratio of these two constant pressure line is 7:1. So P2 by P1, and then P3 by P4. This pressure at P2 and P3 is the same, P1 and P4 is the same. So P3 by P4, that is given, that is 7. Next, to find its efficiency. efficiency is 1 minus 1 over P gamma minus 1 divided by gamma. And what is the gamma? Gamma is the value is 1.4 for the working fluid in this case. So just put the values. What is RP? That is 7, 0.4 divided by 1.4 efficiency. After doing the calculations, you will get 1 minus 1 divided by 1.745. After doing its calculations, you will get this value. I'm not doing the calculations because the part of doing the calculations is very person. So here is issue of this problem. You must find work that is delivered by the turbine and work that is supplied to the compressor or to run the compressor to compress the working fluid. Okay, so first you will find the work delivered by the turbine, then work that is delivered by the turbine. That is our need to get the work output in order to complete the cycle. So that is equal to Cp. So the temperature at the inlet of the turbine is T3 and the exit of the turbine is T4. So T3 is so I can write here that is 1033 Kelvin. So apply the isentropic equations to find the T4 value. So P3 divided by P4, that is gamma minus 1 divided by gamma. So put the values, that is 7 gamma. Gamma is 0. In this case, when 1.4 minus 1, you will get 0.4 divided by 1.4. That is T3 divided by T4 is so after doing a calculator, you will get its value is 1.75, 1.745. So the value of T4 is need to be calculated. So just T4 divide 1033 because T3 is 1033 Kelvin. Divide it with 745 to get the T4 value. So T4 value you will get that is 592 Kelvin. Okay. So here we get the T4 value, that is 592 Kelvin. That is required to find the work delivered by the turbine. So here Wt is equal to Cp is 1.05, and then what is T3? 1033 minus what is T4, that is 592. So after doing the calculations on the calculator, you will get the work delivered by the turbine, that is 443.2 kilojoule per kg. Okay, so next is to find the work output. Now next is to find the work that is required to run the compressor, that is Wc, and that is equal to Cp, and this temperature difference of T2 to minus T1, so T2 minus T1. So in this case, T1 is given as in mentioned in the statement, that is 293 Kelvin. Find the temperature T1, we applied the isentropic equations. T1 divided by T1 is equal to P2 divided by P1, and I already mentioned you that P2 divided by P1 is equal to the pressure ratio, and here that is given in the statement is 7 into gamma value is 1.4 minus 1 divided by 1.4. So by putting the values, T2 divided by T1 is equal to 7 into 0.4 divided by 1.4. So this T2, by doing the calculations, you will get T1 into 7. And after doing these calculators, you will get its value 1.745. Now T1 value is already given, just simply multiply 293 with the value 1.1745, and you will get the T2 final value, and that is 511.3 Kelvin. So this is the T2 value that we need to calculate the work that is required to run the compressor. So put that in this equation. So T2 is now finds, and T1 value is given in the statement. So the work that is required to run the compressor is CP is 1.005, and T2 is 511.3 minus 293. So it's very simple per kg, and the work that is required to run the compressor, that is 219.4 kilojoule per kg. The net work, that is equal to the work delivered by the turbine minus work consumed by the compressor. So work delivered by the turbine is 443.2 minus work consumed by compressor is 219.4. So just do subtraction on calculator, you will get the net work, that is 223 kilojoule per kg. So what is the work ratio? We are about to near its end. So the work ratio is equal to net work divided by gross work, or work that is done by the turbine. So the net work is 223.8, and the gross work, or the work done by the turbine, is 443.2 kilojoule per kg. So just by doing this on a calculator, you will get the work ratio, that is 0.505. That is all.